So, good afternoon, everyone. It's my great pleasure to welcome Philippe Naveau to our departmental colloquium. He is currently at French National Research Center since 2004. Before that, he got his PhD from Colorado State University under the supervision of Richard Tweedy and Richard Davis. He spent a couple of years at NGAR as a postdoc, and then CU a couple of years before joining what is that? The small LSCE. I don't want to pronounce that one. So, he is quite a well-known figure in extreme value theory. He has been serving, or he has already served as an associate editor for different journals, top-tier journals, including Annals of Applied Statistics, Extremes, Journal of Climate, Water Resources Research, etc. So today he's going to talk about analysis of extreme climate events by combining multivariate extreme values theory and causality theory. Right?
So it's always a pleasure to be back in Colorado. Very nice today. Maybe we'll see this weekend. This is joint work with Anna, Alexis, and Julien. And basically, the story I want to tell today is how to, if someone comes to you, I work in a research climate lab, and often people come to me or to my lab and say, oh, we have extreme events, is it due to climate change? That's a question, a recurrent question. And so, first I'm going to give you the motivation, and then we'll see later on how will fit with multivariate explanation and causality theory. So my talk will be divided in 3 parts, but basically here I'm going to speak about the motivation. Then I'm going to assume that most of you don't know anything about extreme value theory, so we will look at univariate case, and then at the end I will look at multivariate cases. So the first point maybe is to, maybe it's obvious to everyone, that is to talk about no stationary in climate science. And to start that, here I just show you from 2016 to 2019, the CO2 concentration in Hawaii. And you can see the seasonal cycle here, and it should come up. So here I'm just going to speak about seasonality. I'm going to look at large scale. And just to give you a representation of that, here you have to see the green line. Here is 400 ppm of CO2 carbon dioxide concentration. And you can see from 1960 to 2015, there is an increase, and you can see the seasonality. Okay, so, but you could look back in the past and say, well, what's happened if we reconstruct data in the past, like some people might do that from high school, and then you have a trend like this. You can see, oh, you can see the no stationarity, and then here it's 1700 from 2000. Another way to look at this is to say, well, let's go back in time. Maybe it was different before. Here is 10,000 years. Okay, so here you can see still the level of today, basically. We are above 400 today, but you still have this reference. And now, if you look from high school data, here it's 800,000 years. Okay, so you can think about human civilization, like where are the Egyptians and stuff like that, and before here, basically. So, well, I show this graph just to show you that here we have a system, the Earth system, and then you have what's called a forcing, like CO2 forcing, that's going to impact the system. And we are wondering how this is going to impact the atmosphere and the climate. And so what you can see here, it's like the rate. It's not the fact it's very high here, but also the rate of change. It's super fast. What we are doing is really triggering something very rapidly. So during my talk, I'm going just to come back to this time period here, but it was just to give you kind of the big picture of what's happening today. And so, because we know we are changing the input of the climate system, then people ask, well, if you have a system, you have the input, you have the output, the climate, let's say. And then you ask yourself, well, can I detect first if I change the input, how can be detected in the output? And also what you would like to say, oh, if I see the change in the output, can I attribute this change to the input? Or which input? So that's called detection attribution. And I like this field because it's an intersection of statistics and climate. I'm not a climatologist, but I know someone in the room who is a climatologist. So he could help me for that. So let's be more precise about what that means by attribution. Okay? Attribution means, first, you need to assess whether the observed changes, like in temperature, for example, are consistent with what you expect. For example, if you increase CO2, the greenhouse effect is going to lead to a warmer climate. That's what you expect. Or if you have a big eruption, you expect a cooling. So there is. But also, to attribute, you need to be inconsistent with alternative explanation. Okay? So it's like if you are interested by studying lung cancer, you need smoker and non-smokers, okay, to see the relationship of the impact of the cigarette. There is an issue with that. As you know, when you look at the Earth, we have only one Earth, I mean, to my knowledge. So in some sense, it's like we have a smoker, but we don't have a non-smoker. Okay, so if I need to create a non-smoker, I can only do that with numerical models. Okay, so most people who work on this attribution problem, they create climate models, and then they change the input. Like that, they can say, I have a smoker or a non-smoker. That's the same kind of idea here. So far, so good. I can answer a question along the way, but this is just a picture to show you what's happening here. So you have the system, the climate. Of course, there is a big part here, we don't know too much about it, but we know a bit, but it's complex. It's international variability. Even without change in CO2, you will have ups and downs in the climate. You have the anthropogenic forcing, which means that what the humans are putting into the atmosphere, that's us, basically. You have the natural forcing, it could be like volcanic eruption and stuff like that. And so you have model error because also your climate model is wrong, like any models are wrong, but it doesn't mean it's useful. It's still useful, but you have model error here. And so, as I said, people play the game when they do runs with everything, which is called historical forcing, basically, and then you do a run, let's say, with only natural forcing. So that's the motivation. And this is called also the counterfactual. So now I'm going to say a few words in terms of causality theory. There is a lot of different ways of doing that. Here, going back to what I said before, in fact, if you want to solve causality, one possible definition is if you remove the cause, then the consequence should be not there. So that's a definition due to Hume in 1748. What we did with LSCE and Philippe, we look at the causality in this way in terms of oriented graph. So I'm going to come back to that later on. But basically, what you need to know about that for this talk is the following thing. It's like, it's possible to make the difference between a necessary and sufficient causation. Okay, so maybe the best example is to look at an illustration. Like you can say, like, clouds are a necessary cause of rain, but not a sufficient one. You can have clouds of rain, but not necessary. Okay? But if it rains, then it's a sufficient cause for the road to be wet, but not a necessary one. Okay, so you can play with that, this kind of definition. Here are statements which are deterministic. But what we want is to put that into a probability framework And that's what Juliet Pearl with colleagues have done in the past. So that we will speak about necessary and sufficient causation in my talk. So now, I would like, the first part of my talk was about the motivation, the climate. Now I'm speaking about causality. Let's put them together and see what people have done in the past. Basically, it started in, this field started in 2003, because in Europe there were a big heat wave, and then people asked a question, well, it was an experiment, the heat wave, it was never seen before, and so people say, oh, what is the probability to witness this heat wave today? Okay, and they call that this probability P0. Okay, so the yes, no, sorry. It's P1, sorry, because P1 is the probability of exceeding the same threshold in a road that it is. So like today. P0, sorry, it's a counterfactual word. It's when you don't have automatic forcing. So people will look just at this quantity. In some sense, you can think it's just a relative ratio. You can say you do P1 minus P0 divided by P1. And in terms of statistics and math, there is an issue here because to witness a heat wave like in 2003 in the factual or counterfactual world is still very low. So here what you do 0 divided by 0, basically. Which in math is not very good to do. So what's mean in terms of statistics, you have a lot of uncertainties. So that's a question here. So that's Peter Stott and colleagues who did that for the 2003 wave. And then, in fact, if I want to make the link with causality theory it's very complicated, but in our case, it's fairly simple. Okay? And why is it's much simple in our case? Because the forcing we assume is external. Okay? Sometimes we can have feedbacks, and that's really difficult to determine the cause, but in our case, it's called external forcing because, like volcanic eruption, we don't think the volcanic eruption are produced by the climate. So, like volcanic forcing is due to the Earth, not the atmosphere. So, and also, basically, we know that the forcing is increasing. Like I showed very much at the beginning, the curve of CO2, we know it's increasing. So, in this sense, the probability of necessity can be simplified to 1 minus P0 divided by P1. That's what I said before, just the definition I said before by Peter Stott and Michael. But they call that the FAR, a fraction of attributable risk. But in fact, it's also the property of necessity. What's interesting with P0 and P1, you can also compute PS, and it's just 1 minus P1 divided by 1 minus P0, and PNS, which is a probability of necessity and sufficiency, which is P1 minus P0. If all this is right, if P1 is better than P0. So that's, so at the end of the day, the message you have to get here is, if you get P0 and P1, then we can compute this quantity, which is good. So now, how can we compute P0 and P1? So here I'm going to introduce a few notation, but classical notation instead of statistics. As I said, there is always a counterfactual and a factual. Okay? And so, to remember the notation, F will be the factual. G is going to be the counterfactual. But you can think about Gaia, for example, for G. And so we have P0 for the counterfactual and P1 for the factual. Okay? And so now I give you U, for example. It's maybe the temperature in Paris during the heat wave. And you want to know what is the probability of Paris is greater than U if we do not have any forcing, ultraviolet forcing, and you want to do the same computation with that. in the factual. So, just to give you an idea, this is just a graph where I take x, a normal distribution, center 0, 1, and the standard deviation, and I just translate by 1. And I compute this ratio here. You can see this is the green curve, and it goes to 1. Okay, so the higher the threshold, the higher is the far, or Pn. Okay? For the exponential distribution, it's the same. For the beta distribution, it's not exactly the same. But most people will say, well, you know, everything is Gaussian, so I should go to 1. Okay? Of course, not everything is Gaussian. And here, there is a statistical theory called extreme value theory, and we give you, how many people of you know, can you raise your hand if you know Gamble, Greyhound, and Fresher?
No, the first one?
Yes, personally.
No, I mean, I've heard the name.
You know the name, but what's important to know about extreme value theory is if you take the mean x bar, you take a sample and you see the average. If you renormalize correctly this, you can show it's going to converge to this distribution, to a normal distribution. If the variance is finite. If the variance is not finite, it's alpha stable. So that's what you have. But you could say, oh, here, I'm not interested in the mean, I'm interested in the max. So if I replace the sum by the max. So if I say Mn, it's the max of x1, xn. So then I can ask myself, if I rescale this a max now, does it converge to something? The answer is yes, which is kind of surprising under certain conditions. It converges to a generalized extreme value distribution, GEV. The GEV distribution has this property that if you take two GEV, it takes the max of them is still a GEV. Okay, like the Gaussian distribution, if you take a Gaussian distribution, you add the Gaussian distribution, it's still Gaussian. So for the Gaussian distribution, you have linear sum stability. For extreme, you have the max linear stability. So these results are kind of old. In the 1D case, 1943, and clinical, and Fisher and Tippett in 1928. So that's a 1D case. You get that in the relative right context, but I will come back to that later. So now,
so Philippe, the other connection is, doesn't the GEV combine the distributions of all three of those guys?
Exactly. So, yeah, it's a good point because I forgot to say the GEV is really like the mother of the tree. You know, you can derive the tree. So it's a very rich family. In fact, here it's the same if you say alpha stable distribution. Because normal distribution, it's an alpha stable distribution. But now look at my curve now. I replace x now not by normal, but now by a gumball. And I translate by 1.7, for example. It goes, it increases, but it doesn't go to 1 anymore. Okay? So for example, if, what that means in practice, that means with the gumball distribution, it's impossible, in some sense, except if this is equals to 0, to have Pn equals to 1, or the phi equals to 1. The same with the fresh air of the value. So you can see that now, if you think that I'm looking at the largest value of the sample, then the far of you will be kind of different than if I do it under the assumption that it's a normal distribution. So it's very important to choose a right distribution because the number could be quite different. So now I'm going to apply this kind of idea to records. And let me define what is that. So it's very simple to define what is the record. It's just to say that today, or tomorrow, will be maybe this weekend will be the slowest day ever recorded in Colorado, maybe? I hope not. If tomorrow will be larger than anything observed before. See, that's really the definition of a record. Okay? So, what is nice with this definition is like, I ask two students during my lunch break, what is this probability? And in fact, I can give them the answer now, but they're not here. Yeah, you're here. Good. It's 1 over R. So it's very, so it's no work to do, but if the variables are exchangeable, it's 6. So now, if you come back to what I said at the beginning, if sometime, you know, if a journalist called me and said, oh, today was the warmest day in Paris. So, and I could say already, in the counterfactual world, I can tell you that, even without looking at any data. This is really a nice formula because it doesn't depend on F, the distribution. So it's one of the few times where you want to compute a probability from the data, you don't have to see the data.
What is the reason I would assume they're exchangeable?
Good question. It depends. For example, in my case, I look at annual maxima. So from year to year, like for the last 10 years, let's say, you can imagine they are. Because maxima, annual maxima are pretty much independent. If I was looking at daily maxima, then I would be different because daily maxima are related to yesterday, and to the before yesterday. So because at the annual scale, the assumption of independence is not too bad. So now I'm going back to my problem. I have P0, P1. So now I have a little r here, which means the return time. Okay, so how long I have to look in my report. And so remember I have P0 divided by P1, and I say, well, what's difficult is the fact that if I have to estimate P0 and P1, this is going to be close, both of them are going to be close to 0, but variable. So the ratio could move a lot. Here, I don't have to compute P0. I don't have to estimate P0, it's going to be always 1 over R. So no error of estimation. The only thing I have to do is to compute this one. So, so here I'm in the factual world today, and I'm asking the question, is the probability to observe a record of today compared to the past in the counterfactual world will be different from 1 over R? And if it is okay, then I show that there is a kind of causality connection. So I want to compute this from data. So basically now I have a new FAR, which is called FAR of R, and it's just the ratio of these two quantities. This one, P0 being none. So I just have to compute this. So it's possible to show the following result. So remember the GV? GV was this. So GV, we know it's a good family to fit maxima and large values. So it's possible to show if for the GV has 3 parameters: location, scale, and shape parameter. So if I have a GEV in the counterfactual, a GG in the factual world, and if the GEV has a shape parameter, which is a strong assumption, we have to check if it is true or not, but it is the same, and the same support, which is fairly okay, I'm supposed to say that, then it's possible to show that minus log of G of Z, so remember G is Gaia, the counterfactual, applied to Z, the factual world. So if I define this variable, W, then W has an exponential distribution. So what that means by that, it means that I don't have to estimate the parameter of this or that. I just have to check if this variable here is exponentially distributed, which is fairly easy to do. Okay, so the question, is it assumption correct here in practice? We show some limiting result and stuff like that, but I'm not going to show it here. What I want to show you, if I know that if this assumption is true, then the far of R is fairly easy to compute. It's 1 minus theta, 1 minus over R. So R is given, it's a Newton time. What is theta? It's the mean of the exponential distribution. So what's nice in this approach, I just have to compute one parameter, not three parameters. Usually people think GV on this side, GE for the factual, GE for the counterfactual, and do the computation. Here, I just have to select one parameter. If you don't like my assumption, and you think, oh, it's not exponentially distributed, and the shape parameter of this GV is different than this one, then W, in this case, will not have an exponential distribution, but a Weibull distribution. But I'm sorry to say that this Weibull is not the Weibull of Weibull. Or in some sense it is. Because in engineering, in reliability, the Weibull of the engineer is not the Weibull of the extremes.
Oh.
So they are related, but they're not the same. So when I say Weibull here, it's a Weibull of the engineer. And at the beginning, I was saying it's a Weibull.
Is it a reparametrization or just?
Yeah, it's a reparametrization. But in terms of the interpretation, it's very different. So now we can, in practice, does it work? So here I'm going to look at early maxima of daily maxima of temperatures, which means the summer. I choose a city by chance. I took Paris.
Paris, Texas?
It's not Paris, Texas. You know why? Because I could get data from 1900 to 1930. And I think the quality of the data in Paris, Texas in 1900 was not as the same. So here, I play the game where I look at observations. I didn't look even at numerical model output. I look at the observation and I say, well, from 1900 to 1940, I call that the counterfactual world, which is not exactly bad, just to play. And I say the last 30 years, basically, 1990 to 2050, I call that the factual world. So I test if it was an exponential distribution, and here you can see the field, and here you can see the QQ plot. That's the observing perspective. And we have a test for that. There's a lot of tests of testing exponentiality, and the test was not rejected. So basically, also by using Bootstrap, you can compute the return level. The confidence band. So here, it's a return period, and here is a far of R. So for example, in Paris, the probability of necessity, it's about 0.5. Just from the observation, just for one location. Because I think it's an interesting result, because usually you have to pull together a lot of information to get a significant result. In here, we can get this. So, coming back to the Paris example, here I already showed that here. That's a far, Pn, probability of necessity position. Here the PS, probability of sufficient position. Okay? And of course, think about it. If you have an extreme event, which is very, very, very large, it's on this side here, then if it happens, it's most likely that anthropogenic forcing is the necessary cause of that. Okay? But of course, it's not because you have anthropogenic forcing very high that it's sufficient to have a very strong heat wave. So that's why when R increases, usually it's easy to prove necessity but it's more difficult to prove sufficiency. And PLS is when you put them together. And so what's kind of interesting is like the best return period, if you want to compute the probability of necessity and sufficiency, is not to look at very high return periods, but mostly at small one. And then it's 0.2. You can say it's not that much. But it's 20% to be sufficient and necessary, which is a very strong statement. Of course, we can play with climate models, and here it's a French climate model from Meteos France. And here it's easy to play with the pole forcing and natural forcing. Then you get this map, the probability of efficient and necessary condition, and it's not surprising, I would say, that in the tropic it's more easy to prove this kind of result than other parameters. Maybe with a new semi-psic experiment we will have better result, but that's already something we get here. Okay, so far I've looked only at one time series, either in space or in time. Okay, so now we want to look at multivariate experiments. So now someone with a nice hat here, and a nice beard. Where does he stand now? It's Wilfredo Pareto, and remember I have this result here, saying if I take the mark, I rescale it, then it's going to achieve. You can do the same for Pareto distribution. But instead of looking at the max, I'm looking at excesses above a threshold. Okay? So everyone knows in this room, I'm sure, that one distribution is stable by thresholding. This is the exponential distribution. Okay? So because if you have been waiting for a certain time in the queue, then given that this time, the conditional probability of this being to have wait like 5 minutes, it's also exponential. Okay, so this corresponds to the fact when gamma equals to 0. Okay, so you can do that. But also the uniform distribution is also stable for thresholding. If you take a uniform distribution, given that you have u or x is greater than u, or y is greater than u, then it's still a uniform distribution. That corresponds to gamma equals to -1. And the threshold distribution is also there. So it's good, we have Pareto. That's still univariate. So now the question is, here it's univariate, I fix a threshold, I look about the threshold. But this could be, I don't know, Fort Collins or Boulder or whatever. But now if I have two stations, let's say Fort Collins and Boulder, suppose I transform everything to uniform, and we'll come back to that later on if you want. Here what you want to look at is at least one of the CT, for example, is higher than the threshold. Not the two, but so it's very important to have this part when it's concomitant. Maybe to explain this a little better, you know, like what you don't want to have is to have a systemic risk. That means if you don't capture it, because some people say, like in finance, if you want to be strong, you just have to diversify. But this strategy is good if everything is independent in the extremes. If it is not independent in the extreme, then to diversify is not that good either, because you have a strong dependence. If someone collapses, then everyone else will collapse. Like Lehman Brothers substance collapse, and all the men collapse, and then you have the government to step in. So to get the dependence right for the extremes is very important for many different applications. So the question now is, what is the distribution of this object? Which is much more difficult than the one object. So here a little bit of equations, but basically the first one here, we have already seen it in some sense. Just this one here. Okay, so this one was for one time series, but you can ask the same question if I have 3 locations, Longmont, Boulder for Collins, I take the early maxima. If I rescale them, then it's going to converge to something, and the answer is yes. It's not a GEV, it's a multivariate GEV. And also, it's possible to, you can forget the maxima, it's not very important. What's important here is to say, this you can show that it's equivalent to looking at above a threshold. So, given that at least one of the components is large, then if we rescale this, then it's going to converge to something which is called V. And V is not a Pareto distribution, it's a multivariate Pareto distribution. So now, the question is what is this V here?
So you don't,
Yep.
you're not taking into account the correlation between the observations, right? Because you marginalize the maximum.
No, the correlation is taken into account in the sense that here the result is multivariate. So I don't, maybe we'll come back here later on. You see, here it's a multivariate, when I say board wide, it means Y1, Y2, Y3, YD.
Right, but when you look at the maximum, you define that as the maximum of the vectors, right?
Yes, but it's a pointwise maxima,
Right.
but still. Okay, so suppose you have x1, x2, a normal with a certain covariance matrix. Okay, so if I do a replicate of that, okay, so I can define M1 and max of x1, 1, x1, n, and n2, the max of that. That's 2, sorry, 2, x2. And so n1 and n2 are dependent because there is a correlation structure here. So, but I'm going to speak about the marginal first. So I have this object V, and I have to define what it is. So I have V1, V2, V3, Vd, it's a D-dimensional object. So this, given that I'm above 0, then it's a gamma, it's a Pareto distribution. So the marginals are univariate Pareto, the marginals, by definition. And now, I'm going to speak about the dependence later on. This is a different result.
Yeah, because I thought you would look at projection. That's what I thought you would do.
Yeah, exactly. So here, pretty recently, Olga Outside and colleagues just showed that this multivariate object, I didn't speak about the structure yet, but I'm going to speak about it, has this property. Okay. If the shape parameter is the same for each direction to look at, then given that my projection, so here it's a linear projection, is greater than 0, so given it's large, then it's also a GPD. So it's like the Gaussian distribution, which is nice. The Gaussian distribution has a nice property if you take a linear combination of Gaussian is Gaussian, but also if you condition on the Gaussian distribution, it's still a Gaussian distribution. And here it's the same kind of thing. Here, if I take linear combination of a multivariate Pareto, it's still a Pareto.
And that's how you define the T, right? You look at projections.
We can define like this way, but what's the definition I'm going to give like now is this one here. I think it's simpler to understand. But let's speak about first like this. Here, suppose I renormalize everything to have gamma equals to 0. which is the exponential case. Then, if I work with the exponential case, I can go back to any v. So what I mean by this result here, to explain, not to do things further, to explain, we can assume that gamma equals to 0. Because if gamma equals to 0, then I can construct this. So now from a simulation point of view, if you want to create a Pareto process, then what you need to do, it's very simple, it's really one line of code basically. You take an exponential draw in the 1D, so you draw an exponential, that's easy. And then you take any t multiplied vector you like. I don't know, what do you like? I mean, some people like Gaussian processes, I suppose. Or you take a kernel of Gaussian processes or whatever. So you take that, and then you subtract the max of its coordinate. Okay. This, it's a max, it's a GPD process. That's very, in fact, that's very simple to prove. What's much more difficult to prove, and I didn't do that, someone else did that, is to show that any generalized Pareto process has to be written like that. So, but what's nice here, the formula is very simple, it's very general, and in fact, one drawback in terms of difference is too general, because t can be anything. Okay, so if I want to model something multivariate, it's nice when I have a parametric form, but here, let's say anything you put in will give me a generalized Pareto process. So in the general case, you can rewrite the density, if you suppose they exist, like this. But most of the time, people in practice say, well, what kind of t I can put here? And the thing more, and they say, oh, the Gaussian distribution. Because it's very simple choice. So that's what we did here. So here, we create a GPD process from a Gaussian process. I mean, here I look only at the Barrett case, but you can do it as a process. And so now my density is this one. So you can recognize the sigma of the Gaussian process and this kind of thing, but it's not a Gaussian process. It's a Pareto barrier distribution. And we have the expression, and that's, if you simulate, that's what you get. So here I have a correlation of my Gaussian process equals 0.4, and then you get this kind of plot. So you can see above the threshold, here I fix to 0, then you get this kind of dependence. You will never be able to do that with a Gaussian process. A Gaussian process, by definition, has tail which are independent. Even if you take a correlation of 0.9. So to get a point like that in the Gaussian process would be impossible. So, and here two different ways of looking at the. So now we have an object where we can play with but remember, we were talking about causality. So now I would like to bring multivariate GPD and causality together. Okay? So I think you have forgotten what was the formula here, so I put it back. So you go 1 minus P0 divided by P1, and that's the probability of necessity, probability of sufficiency, and probability of necessity and sufficiency. So that's what we have. Good. And so now what we like to do, in some sense, is to project, so I could be 0 close to 1. So like P0 of V. What we want is like, I don't know, I think all of you know what is a PCA or here or EOF. Usually when you do an EOF or PCA, you try to look at direction of interest where you have observations of variability. here we have the same idea. We say, well, now we know that a linear combination is going to be Pareto. So if I have y1 and y2, maybe I can do a linear combination of that to maximize my causality. So that's what we call optimal projection. And what we want to know, for example, can I find the weights that will maximize either Pn, Pns, or Ps? Okay? So V star would be for Pns. Or you can do also arcmax also on V. So it depends on what you want to play with. You can either optimize respect to W or V. So what we need to do, remember that's a definition of the process. When T is Gaussian here, you have an explicit formula. When it's not explicit, you have this usual formula here, which is kind of ugly, I have to admit. But we have it. So that's the case where we have a normal distribution as an input. And so PNS in this case is pretty simple. So which is good in some sense, like if we want to have multivariate extremes, and if we want to compute PNS with respect to projection, we have a fairly simple formula. There's no integrals or stuff like that, which is convenient. And if you want to maximize PNS with respect to V, for example, the threshold you have to choose to maximize this, you can find it explicitly. So let's see in practice, and after I'm almost done. Here is to show you different cases of projection from a variant case, where you look at Pn and PNS, Pn, PNS, PNS, and either we try to maximize here, for example, with the dotted curve here, you maximize to 0.2. If you take any weight, some weight, it's lower, because we know that's a max. So in some sense, you can maximize PNS to show the causality. That's basically what I'm doing here. Here I have a quick graph about, I took weekly maxima of precipitation. Precipitation is a pretty difficult object in terms of distribution. And then we look at thresholding of this, we project that, and we get this kind of map about Pn. Okay, so here you have a probability of necessity, which is fairly high here, but overall it's around 0.2 here. So you can do this kind of thing here. So I'm almost done. So what I tried to tell you in terms of statistical probability that we can make now some link between multivariate extreme value theory and causality theory. So we can find optimal projection in some sense. You knew that. That's an issue. I think there is some, I mean, what I mean by that is that to look at the mean temperature is really not very interesting anymore. We know it's getting warmer. What is important, I think, is really to look really what's happened with multimodals in terms of climate, look at extreme uncertainty and stuff like that. Also, the dimension of the object. It's at the global level, it's fairly easy, but you look at very localized regions, it's much more difficult. We try to show it's possible to deal with recurse, even with observation. The second part was about, I didn't speak at all about the inference, but if you have questions about the inference, you can speak now, or you can send me an email. And here I assume that I have exactly a multiple GPD, but remember this, it's a convergence theorem. So what's happened when we are not exactly at the end of the convergence? So that's also a question. And we apply a little bit our model to the climate output, but I think it would be much better to do it not only to one climate, but 2 or 3 climate models out. And I think I'm going to stop here.